Okay, so to take a look at this example here, we have the point minus 9 written over here. And what we want to do is take this point minus 9, minus 9. We're going to use this point minus 9, comma minus 9, and we're going to write the equation of a line. This line, according to these words here, is supposed to be write an equation in the line passing through the given point and satisfies the given conditions. Okay, so it's going to be parallel to this line. So what we really need to do is take this equation right here, the first equation, we'll figure out its slope. So let me write that equation. We have minus x plus 9y is equal to 36. Okay, so then what we can do here is we can add x to both sides of this equation. So we end up with 9y is equal to x plus 36. And then we're going to divide through by 9, divide through by 9, divide through by 9. And what we'll end up getting here is the equation that y is equal to 1/9 x plus 4. Because 36 divided by 9 is 4. Okay, so this equation tells us right away, of course, that m is equal to 1/9. It's in slope-intercept form, where m is the slope right here. So what we're going to do is say, we'll just go ahead and make a note of this, that m is equal to 1/9. Now what we can do at this point is we can get rid of this work, because now we're going to start a new part of the problem. Okay, so now that we know these conditions here, we're going to move down and use this equation, which is referred to as the point slope equation right down here. Let's see, point slope, where we take this point, so we put y minus 9 is equal to the slope of 1/9 times x minus 9. Now in this case, they're both minus 9s, and notice that both of these create the double negative. You could have wrote y plus 9, but I just wanted to show you why it is that way, so we can just clean this up a little bit. We have y plus 9 is equal to 1/9 x, and then minus, 1/9 times 9 is, well, that's plus 1. And this is a 9 down here, sorry, to make it look more like a 9. And then we just want to go ahead and subtract 9. Okay, and we have, for the answer for the y equals to 1/9 of an x, plus, let's see, 1 minus 9 is negative 8. Okay, so this right here is the answer for the first part A, slope-intercept form. Slope-intercept form says y equals mx plus b. See, we have 1 take away 9. That's where this 8 came from. Okay, we still need to put it in standard form, though. So we'll go ahead and take this equation, 1 minus 1/9, or equals 1/9 x minus 8. And we'll multiply through by the common denominator on the bottom to get 9y is equal to x minus 72. That's multiplying every term by 8. 8 times 9 is 72. And then we'll move the x over by subtracting it, so we have minus x plus 9y is equal to negative 72. And notice here it says that a must be positive, and here I have a as negative, so just multiply everything by minus 1, and you get your answer x minus 9y is equal to positive 72. And that is the answer to the second part right there. Okay, that's an x, and that's the answer to the part about the standard form. There you have it. Okay, let's take a look at this next example. We have graph the intersection or union as appropriate to the following pair of linear inequalities. And notice it's and, so this is going to be the intersection one. That means basically when we shade each inequality, we're going to find where they overlapped. Let's start with x plus y is less than or equal to 5. So over here I have x plus y less than or equal to 5. Okay, we're going to start out by making that x plus y is equal to 5. We're going to change it to the border, and then we can say y therefore is equal to negative x plus 5, where we know that 5 is the y-intercept, that's here, and that the slope goes negative 1, so we have m equals to negative 1, so that's down 1 over 1, so we're going to get something like this, and we can go ahead and put a line through those points. Okay, so we went ahead and put a line through those points as I've shown you here. Now let's take this test point 0, 0 and try it. So we take 0 and we'll put it in here, plus 0. Is that less than 5? And the answer is check. That is definitely less than 5. So we're going to shade, and let me use a different color for shading here so you can see this. We're going to go ahead and shade this whole entire side right here. We'll shade all of this side. Okay. And now we need to look at the line x equals to 2. So let me come over here and look at that. X equals to 2. We'll get that color changed back here. Okay, it actually is greater than or equal to 2, but the border is x equals to 2. And notice that x equals 2 is just a vertical line through 2, so let's put one of those in. Okay, that is the x equals to 2. And of course it says greater than 2, so we're going to shade, and I'll get the color for shading. We'll use a little bit different color shading here, and we'll shade it this way. This is greater than or equal to 2 over here. Okay, now because this is an and, we need to see where these things are going to intersect. And that's this color down here. So what you then do is you grab yourself an eraser, and you just go ahead and start getting rid of all the other ones, and we can do that here. Let's see if I got this eraser to work. Maybe. I'll try it here. And we want to get rid of all of this and so forth. Okay, so I've erased most of what I wanted to do there, and let me just grab a different color here. What we need is to shade in basically this part right here, which is going to be our answer. So when you get to graph this on MyMathLab, what you want to do is just leave this part right here shaded. This right here inside this little triangular region is the actual answer. Now you should ask yourself, should you have a straight line or a dashed line? Since both of these equations have equal to signs underneath them, both of them will be, that's the blue one here, which is hard to see because I use the same color shading, and the black one here. Okay, hopefully that helps. Okay, we have yet another example here. Let's go ahead and see that this one has an or, so that means when you shade it, you don't find the intersection, you just keep it. And we have y is, well, greater than 2. So if we look at the line, which is y is equal to 2, y is equal to 2, that's going to be a horizontal line through 2. Let's do that. Okay, so I went ahead and put that there. Now what you want to also know, though, is that because this is only greater than and not strictly greater than or equal to, I mean strictly greater, not greater than or equal to, you're going to want to make this a dashed line, so it's going to look more like this here. If I can make some dashes in there, you can do better. There's an option in MyMathLab for actually just making it a dashed line. And again, the reason of making it dashed is because there is no equal to sign under here. Here at y is greater than 2, of course, that's going to be everything above the lines here. So it's going to look something more like that right there, where you have the lines just going above it. This is shading. If you want to shade, that's fine. You know, you could do shading like this, however you want to do it. I'm just trying to keep it simple. Okay, so all this shading up here is above the line. Oops, I went down below it. Sorry. Let me fix that, if I can fix that. Yeah, and we'll go ahead and do this. Good enough for what we're doing here. Okay, so the next equation over here says that y minus 2 is greater than x minus y. Here, I'll just write it. Let me just go ahead and write it here. We have x minus y. Well, we'll look at equals to 2 because here I have subtract x, subtract x. Here we get minus y equals to minus x, that's an x plus 2. Or that y is equal to x minus 2 when you multiply through by negative 1. That has a slope of 1 and a y-intercept of negative 2. So we'll go here for the first point, and then we'll go to the second one, which is a slope of 1 up. And let me go ahead and put a line in there. Okay, now we have to decide what side to shade. So let's take the first original equation down here. We have x minus y is greater than, let me get my pen working back here again, sorry. Get rid of what I just did there. Okay, so x minus y is greater than or equal to 2. And notice this point 0, 0 is not on the line. 0, if we put in 0 for x and 0 for y, 0 is not greater than 2, so we want to shade everything on this side. So we'll go ahead and get a color here, and then we'll shade it all on this side like this. I'm just shading all the way up here. It's supposed to be on the sideline, but so basically now, because we've shaded this side of the line and we didn't use it because 0, 0 didn't work in there, that means none of these points. The last thing we do is look at the fact that this is an equal to, so therefore this is a solid line. This is strictly greater than, so dash line. And since it's an or, we're done. That's your answer right there. Okay, for this example, it says determine whether the relation here, the relation is a set of ordered pairs, defines a function. Well, see, we look at minus 9, 6, and then minus 8, the x values. So let me write that over here. We have basically just the x values to consider here. X values are, x values equal minus 9 and then minus 6. Oh, no, it's positive 6. Sorry, I didn't see it's kind of small. So it's minus 9, then we have positive 6, and then minus 8. I'm just looking here at the x values. Do any of those repeat? No. So this is a function. So yes, because no two ordered pairs are the same, or yes, because no value of the first component is associated with more than one value of the second component. That's your answer right there. You cannot have repeated x's in your functions, but you can have repeated y's. Okay, so we have a second function example here. If we look at the ordered pairs that are made here, we have 15, comma, what is that, 14? That's right there. You see 15 maps to 14, and then we have 19 also. Oh, that's a 16, isn't it? Yeah, I should probably get some glasses, I think, or make my numbers bigger. Let's get back in here. Let's make that an actual 16. That's a 16, right? Isn't that a 16 right there? Yes. Okay, so there's one ordered pair. And another one would be 19 to 16. Okay, sorry for that funky looking 9. Let's see if we make that a little bit better, 9. And then the other one is 4 to 2. Okay, so that's what the ordered pairs would look like. And as you can see, 15, 19, and 4 don't repeat. So yes, this is a function because all elements of the domain No, it's this one here because you are allowed to have repeated values for the y. So the answer in this one would be D. Okay, this will be the final one for this homework here. Determine whether this relation defines a function and give its domain and range. Well, every x has an exact y associated with it. And if we had an x, let's just pick one. Let's say if we had, well, 0 is an x, right? That's not a good 0. And it's associated with the number 2, just like looking at the graph. There's the point 0, 2 right there. Okay. Now, if you had 0 and some other number, then we would have a repeated x. But of course, you'd go 0 and you'd have to have a point somewhere else other than 2. As you can see, that would make a vertical line hit 2 points. And that can't happen here. So we use something called the vertical line test to look at this and say, yes, this is a function. Yes to function. Now the domain, of course, it goes all the way to the left and right on the x's and all the way to the left, right, and y. This is your domain. Your domain is x and your range is y. And so we can say that the domain is going to be, you can do it in minus infinity to infinity. Oops, sorry, there's an infinity sign. Using the notation called interval notation, or you could say minus infinity is less than x is less than infinity. And that's how you do an inequality. Now the range itself would actually be identical because they are exactly the same in this case. It's not always the case, so the range would look like this as well.